you can go first.
Right, good afternoon, everyone. We'll go ahead and get started. Before I make my announcements, I would like to invite Cody Evans, who has an announcement of broader interest to make.
Hi, Cody Evans. I'm a second-year MBA at the Macomb School. I'm also president of the Adam Smith Society, and this next Tuesday we're hosting a debate that I think may be of interest to a lot of people in this room. So we've arranged kind of like a clean energy debate around the idea that clean energy can drive America's recovery. And so we'll have Colin Meehan, who spoke here earlier in the semester, come and debate in support of that statement. And debating against him, against the statement also, will be Robert Bryce from the Manhattan Institute. We have Mitch Jacobson will be moderating for us, who's from ATI and IC Squared here at UT. So it should be a really fun event. We've got a bunch of MBA students, law students, LBJ, and then anyone else who wants to come. So we'll be over at the AT&T Center in room 105 next Tuesday at 5:15, and then we'll have a reception right after. The debate should end about 6:30. So if you have any questions, just email, I guess, Trevor, and he can get you my contact information. Thank you.
Can you say the time, date, room again?
Yeah, so we'll be at the AT&T Center in room 105 at 5:15 p.m. next Tuesday on the 18th.
Awesome. Thanks, Cody. Before I introduce our speaker today, let me tell you who is going to speak next week. It's Gus Lott, who is a senior engineer at Yarkomink, who will talk to us on cybersecurity in the electricity grid, which is becoming a very, very important issue. We have talked about a bunch of other issues related to electricity, but not about increasing cybersecurity concerns and infrastructure needs. So it should be a very interesting talk. It's a great pleasure to introduce my colleague and our speaker today, Dr. Dave Allen. Dave is a professor in chemical engineering. His research over the last decade or so has focused around urban air quality issues. He led the first and second tranches of the Texas air quality study, which was one of the largest studies of its kind ever done, which involved hundreds of researchers across the country and internationally, and it has had huge, broad impact on how we think about air quality management and regulation here in Texas. Currently, he is using the results from that study to provide sound scientific basis for how we think about these issues moving forward. And part of his talk today is what was published in the Proceedings of National Academy of Sciences last year on a very, very important issue of methane emissions in the supply chain of natural gas production from shale. Welcome, Dave.
I guess the microphone is on. I'm hearing it pretty loudly. So this is a talk that over the last year I've given all over the world multiple times in various forms, but this is the first time I've done it here at home. So it's nice to have the opportunity to tell you a little bit about the work that we've been doing over the last several years. I'm going to go through some introductory material that I always go through, not assuming that people know a whole lot about shale gas, although that may not be the right assumption for this audience. So bear with me if some of the material at the beginning is introductory, and then we'll jump in. So I think many of you know about the dramatic changes that we're seeing in the energy landscape, primarily here in the United States, but broadly in North America, driven by the ability to use technologies such as horizontal drilling and hydraulic fracturing to access gas and oil and shale formations. And these are data from the Energy Information Administration that show the growth in shale gas and project future production rates for shale formations, with the United States becoming increasingly reliant on shale gas for its natural gas supplies, but also with the oil that comes from these formations as well as the gas, catalyzing a number of really pretty profound transformations. I've been working in the intersection between energy and the environment for the last 35 years. And these headlines are something that I perhaps thought I would never see. The International Energy Agency 2 years ago predicting that the United States would become the top oil producer in the world, surpassing Saudi Arabia within 5 years. That has already happened. And so this transformation that we've seen from the development of these shale resources is just absolutely profound in the energy sector. It's primarily happening in North America, primarily in the United States, but the entire world is watching what happens because these resources and the formations are not restricted to the United States. So what you have here again is estimates from the Energy Information Administration. Shown in maroon are various basins where resource estimates have been made. Shown in tan are known resources where the estimates have not been made by the Energy Information Administration. And then, of course, if you look at this graph carefully, you'll note that all the formations end at the seashore, and that's clearly not the case. So there are many reservoirs and basins that aren't represented here. Nevertheless, taking these ones that do have estimates, what's the potential around the world for this resource? And these are estimates, of course, a lot of variability in those estimates, but let's just take a look and let's focus on gas. Again, these are from the Energy Information Administration, released earlier this year. And what you see is although much of this activity has been occurring in the United States, the United States by no means has the largest resources. Currently, it's believed that the most extensive resources will be in China, followed then by Argentina, other places around the world. Again, these are estimates, but the extent of the resource, I think you can appreciate by noting that these are the estimated recoverable resources based on the analyses done by the Energy Information Administration, 7,300 trillion cubic feet. Total natural gas consumption worldwide today is about 100 trillion standard cubic feet per year, more or less. So a huge resource. And this transformation is happening really rapidly. I've already pulled these up, but I'll leave the slides, and if you want to get these links later, you can see the links. But I'm going to show you two basins in Texas where the Energy Information Administration has taken data from the Railroad Commission of Texas and plotted the development of wells. So let's first look at the Barnett Shale Formation in north central Texas, so a little bit north and west of Fort Worth, although you'll see it developing around the city of Fort Worth. So here's the area represented, and here's the metropolitan region of Fort Worth. What you'll see here then are a series of black dots. Each black dot represents a vertical well. Each red dot will represent a new horizontal well with hydraulic fracturing accessed using new technology. And let's watch the development between 1997 and roughly 2009 and how it evolves. So let's watch the animation. So 97, 98, 99, 2000. Some of you may recall that gas prices hit a spike in about 2005, then again in 2008, and beginning right around 2005, you begin to see a lot of horizontal wells appearing. And then again in 2008, by then, really extensive development. Okay, so it's not just the Barnett Shale where this is happening, so roughly 10,000 gas wells, 20,000 total wells in the Barnett. This is also happening in the Eagle Ford, so let's look at what's going on in the Eagle Ford. And again, let me show you the area that's represented here, so basically south of San Antonio. And we're going to watch the development of this production increase over an even shorter time period, particularly between 2009 and 2011. So Initially in this animation, again from Railroad Commission data, essentially just a few exploratory wells in 2006 and 2007, and then 2008, 2009, and then very rapid development that's continuing today. The formation is shown here in 3 color bands representing regions where there's oil, regions where there's oil and gas, and regions where there's just gas. And right now, most of the production is going after wells that will produce both oil and gas. Nevertheless, the point of these slides is this is happening really fast, and it's having a significant impact on energy markets in the United States, which have a global impact. And anything that influences energy influences everything. And so let me just point out a few other things that this natural gas and oil boom is influencing. One is electricity generation. So we've already begun to see in the United States shifting from coal as a fuel for electricity generation to natural gas, driving a decrease in national carbon dioxide emissions. In addition, because we're producing both liquids and natural gas, we get the things that fall in between, which are broadly referred to as natural gas liquids. So compounds like ethane, propane, butane. The abundance of these compounds now in the United States has made the United States one of the lowest cost producers of these commodity chemicals in the world. I'll pick on a large chemical company where the chief technology officer came to the Department of Chemical Engineering here at the University of Texas and told the assembled faculty who were meeting with him that their company would never build another chemical manufacturing facility in the United States because of the costs of ethane, propane, butane. And now that company, as well as many others, are dramatically expanding in the United States. So it's having a dramatic effect on chemical manufacturing. I would argue it will have a dramatic impact on agriculture. The primary cost associated with ammonium nitrate fertilizers is ammonia. The primary cost associated with ammonia is hydrogen. Where do we get our hydrogen? From natural gas. Energy affects everything. These are just a few examples of the dramatic changes that are occurring. So, huge economic consequences of these developments, but there's also an environmental footprint. And here at the University of Texas, we have some of the world's leading experts in many of these areas. So people at the Bureau of Economic Geology and the Mechanical Engineering Department here at UT are studying water quantity, water quality issues associated with these methods of producing oil and gas. At the Institute for Geophysics, some of the best experts in the world on induced seismicity associated with these activities. And so what I'm going to talk to you about is the work that we've been doing on air quality. You should hear from experts on all these areas. This is, in my view, the most important thing happening at the interface between conventional energy production and the environment, and the most important thing that's happened over the last several decades. And we need to look at this very carefully. And so I'm going to restrict my comments just to air quality. It's not that there aren't these other environmental footprints, but this is where I'm expert, and so that's what I'm going to talk about. So when we look at potential air quality impacts of natural gas production, particularly from hydraulically fractured wells in shale formations, there are 3 main categories of impacts that people worry about. And we're only going to have time to talk about one of them today. But we've done a lot of work in all of these areas here at UT. So we could be concerned about emissions of precursors of photochemical smog. So things like nitrogen oxides and and hydrocarbons that can react in the atmosphere, producing the familiar photochemical smog, familiar if you live in cities like Los Angeles or Houston or Dallas or any major metropolitan area. So that's one category of concern. The second category of concern are compounds that by themselves are toxic, so they don't rely on photochemistry to have a toxicity, but are by themselves toxic. And the one that's gotten the most attention here in Texas is benzene. There's been a lot of work done on benzene. I'm not going to dwell on that in my formal presentation. Happy to answer questions about it. But in my view, the air toxics issue is extremely important, but I don't think benzene is the biggest issue. I think that there are a variety of other species that haven't seen a lot of measurements yet. A number of measurements are just beginning to emerge that may wind up being more important. But what I'm going to spend most of my time on is greenhouse gases because it's an area where there's a lot of new information that's just coming out, that's been out just for a year or less. And so let me try and update you on where we stand with the issue of greenhouse gases. So why is it such a tough problem to estimate what these emissions are? Well, hopefully those animations that I showed you gave you a sense of the fact that this is a rapidly changing problem. You can't go out and make measurements and assume the same thing will be true 2 or 3 years later. And the number of facilities is enormous. These are data from the Texas Commission on Environmental Quality for the Barnett Shale in north central Texas. Tens of thousands of wells in one region with varying equipment on each site, varying types of operating practices, and so on. So it's a tough problem. We address this problem by using multiple approaches, and we've used all of these approaches here in Texas. So let me describe them to you, and I'll bin them as bottom-up and top-down. And bottom-up really refers to just one thing, and that's shown by this picture here. This is a member of our team going out, making a measurement at a site, on a well pad, directly at the point of emission, and measuring what those emissions are. Okay? If you want, though, to estimate what the emissions for the Barnett Shale are, you're not going to visit all 20,000 wells. You're going to visit a subset of them. And then you're going to assume that your sampling is representative and that you can scale it up. Okay? So that's a bottom-up approach. There are a variety of top-down approaches, and we've used all of these. One is to take some sort of mobile measurement van. This is one particular set of instruments that we've used here in Texas, been used around the world. There are others, but the basic idea is that you get downwind of the site and you measure the plume, and you get a sense of what the entire plume is leaving the site. And so you have an estimate for a single site of what all the emissions are for that site. You can also place a fixed monitor. This is a trailer with a bunch of instruments in it. This particular one is located up in the Barnett Shale. And you can place these monitors in the middle of a sampling region and make all sorts of measurements. And you put it out there long enough and you get lots of different wind directions. You sample data from a large number of sites. You can fly airplanes over the production regions. And you can do satellite measurements. So we've done all of these here at UT Austin with the exception of the satellite measurements, but we've compared some of our data to a number of satellite data. So all these approaches have been used here. All have been used at a few places around the country, around the world. So I'm going to give you a case study of what we know about methane from natural gas production, the emissions of methane, and present it as sort of a case study for the need to integrate all this diverse information that we're getting. So why methane? Number of reasons. One reason is that there are new regulations on emissions of carbon dioxide, largely for power plants, largely driven by the data that you see right here, which indicates that if you want to generate a megawatt hour of electricity from a typical electricity generating unit in the United States, you're going to get something like 2,200 pounds of carbon dioxide emitted per megawatt hour of electricity that you generate. In contrast, natural gas with a higher hydrogen to carbon ratio in the fuel has less CO2 emissions when you burn it than does coal-based electricity generation. And the current standard for both new power plants and existing power plants, for new power plants, the new standard falls at 1,100 pounds of CO2 per megawatt hour that was proposed by the EPA earlier this year. So natural gas has been proposed and in some senses promoted in regulation as a transition fuel to a lower carbon economy. But the problem is that the power plant emissions by themselves aren't the whole story. We need to look at the entire life cycle of the fuel supply getting to the power plant. And the challenge with natural gas production is that we can get leaks along this supply chain. And if we have those leaks, they can have a significant impact on the greenhouse gas footprint of electricity and other fuel use of natural gas. Why is that? The answer is because methane is a potent greenhouse gas. How potent? You see the number 84 here. This is not strictly a scientific question, how potent is methane? It's also a policy question. We can make unambiguous scientific measurements about what the infrared absorption of methane is in certain frequency bands. And from that, say, if we put a pound of methane into the atmosphere right now, how much radiation will it absorb? How much radiative forcing will it give to the planet? We can calculate that. That's relatively unambiguous. It's a well-known number. And the number is 1 pound of methane is equivalent to about 120 pounds of CO2. So where does the ambiguity come in? The ambiguity comes in because methane in the atmosphere reacts. It's attacked by the hydroxyl radical, and it's converted to CO2. The time scale for this is 10 years, roughly. And so if you're interested in the radiative forcing of emissions over a 100-year time frame, then you're going to integrate this carbon in the atmosphere for as long as it lasts, say 100 years. And perhaps for the first 10 years, it's methane, but for the next 90, it's carbon dioxide. Right? So if you're interested in a 100-year forcing, which is generally what the Intergovernmental Panel on Climate Change assumes, then the number is something like methane's 28 times as potent as CO2. If you're interested in today, right now, it's 120 times as potent. So what are we interested in? Are we interested in climate impacts today, over the next century, over the next couple of decades? That dramatically influences how important we believe methane is. If you were just interested in today, then you would say on a radiative forcing basis, methane is about as important a greenhouse gas as CO2 in the United States from our emissions. On the other hand, if you're down here, or use the EPA number, which is currently 21, it's about 10% of the greenhouse gases in their radiative forcing in the United States. So it's not entirely a scientific issue how potent CO2 is. But let's get to this issue of whether or not natural gas could deliver sustained climate benefits. So these are analyses done by Ramon Alvarez at Environmental Defense Fund together with some colleagues at Princeton. And what he did then was to use those different potencies of methane, ranging from 120 down to 28. And he said, what happens if we do fuel switching? What level of leak in the system can we tolerate and still get a climate benefit from switching to natural gas? So let's look at the example of coal. So Ramon's calculations were that if you want to switch from coal to natural gas, if you want a climate benefit today, you've got to get below 2.7% leak in the supply chain. Any more than that, you've lost your climate advantage. If you're willing to wait 100 years, an average over 100 years, you can tolerate a much bigger leak rate. And similarly, you can do the same calculation for other types of fuel switching. But let's just say that the leak rate needs to be between 1% and say 6% if we're going to get any sort of climate benefit from switching to natural gas. Right? It's not entirely a scientific question. A lot of policy embedded in that, but let's just use that number, 1 to 6%. So how much is it? Well, a few years ago, the simple answer was, we don't know. And there were estimates all over the place, ranging from the EPA estimates, which were in the 1 to 2% range over the life cycle, all the way up to 9, 11, 16%. Really huge numbers were out there. Almost all of these numbers a couple of years ago were based on estimates. We had very, very few measurements that had been done. And so a whole series of studies wound up getting done, top down, bottom up, over the last couple of years to really try and nail this down. Some of the existing literature that's been out there on top-down measurements of methane have been summarized in a couple of recent review papers. There was one out of Harvard that got published in the Proceedings of the National Academy of Sciences last year, and then Adam Brandt at Stanford published another review in Science earlier this year. But both of these studies took all the existing top-down data and asked the question, are we getting the methane emissions right? And they both came to more or less the same conclusions, and I'm just citing Adam Brandt's conclusions here. They estimated that we were about 50% too low on what the emissions were going into the atmosphere based on things like aircraft flying around saying how much methane is out there. There was some geographical variability, but this left open the question, all right, we're missing some methane emission sources. Which ones? How much? So we began a bottom-up measurement campaign. This was catalyzed by Environmental Defense Fund. They brought together their organization together with initially 9 mid-size and large natural gas producers. I led the study team, which consisted of our group here at the University of Texas, together with the consulting firm URS and Aerodyne Research out of Massachusetts. And our goal was to make direct source measurements, bottom-up measurements. So I'm not going to describe in detail our measurement methods unless you have questions, but I do want to show you these pictures to give you a sense of what we did. And so among the things we were doing was initially in normal operation, this would have been an open-top tank on a well pad during a process called a well completion. And so what we had to do in some cases was enclose those open tanks. So we enclosed it all and we routed all the gases through a temporary exhaust. We measured the volumes coming off of that temporary exhaust. We had remote sampling capabilities and were able to measure the compositions. Here's a member of our team on top of a tank that had a vent on it, and again installing a temporary stack. Point being, we were going and measuring emissions directly on the source. In all of these types of studies, it's important to say where your funding came from and be completely transparent about that. So in this work, our funding came from Environmental Defense Fund, which also catalyzed the study. and brought many of the initial partners to the table. We at UT brought a few additional partners to the table, but here are the companies that participated with us, and you'll recognize many of the names of these companies. The participation of the companies was absolutely critical to this being a success. If you're going to go and make measurements, and some of these measurements had never been made before, there were no experimental measurements of certain classes of these emission sources, and we had to make sure that we could do those things safely on the site, and then we needed access to large numbers of sites. So the participation of the companies was absolutely critical, and they made important technical contributions in designing safe and effective protocols for making these measurements. So the study team was the University of Texas and included URS and Aerodyne. We knew that no matter what we found, we would be subject to extreme criticism, no matter what. And so right from the outset, we formed an independent advisory panel that gave us comments on our study design, on our sampling protocols, on our initial data collection, on our data analysis, on our final presentation of the results. And that was in addition to putting this out in the peer-reviewed literature. So we tried to be as scrupulous as we could be in setting up levels of review and transparency. What we did was measure this part of the supply chain. So the oil and gas production part of the supply chain. So up to the point at which the gas left the well pad. What's going on right now is that a whole series of other studies are being brought to completion. Again, catalyzed by Environmental Defense Fund, operating with other companies, operating in different parts of this supply chain, looking at gas gathering and processing, looking at national scale transmission, looking at local distribution, and looking at some uses. So we were the first ones to get our results out there, and I'm going to show you some of the things that we found. We sampled all over the country. These are American Association of Petroleum geologist basins, and these are the places we sampled. Whenever you do a bottom-up study, what you have to do, since you're going to measure directly specific sources, is you have to decide which ones you're going to go after. At the time we started this study, the most recent information that was available about what the emissions were from well production sites is summarized here. It came from the US EPA and what's called the National Greenhouse Gas Emission Inventory. And the estimate was that there were annual emissions of about 45 gigograms. Biggest single contributor was something called a well completion flowback. Again, I'd be happy to answer questions about that at the end if that's something you're not familiar with. But this was the distribution. And so we went after the largest of these sources. The one we spent the most time, effort, and money on was well completion flowbacks, in part because it was considered to be, at the time, the single largest source in the entire natural gas supply chain of methane emissions. There was the greatest uncertainty in the literature about exactly what these emissions were, and there were absolutely no measurements. So we spent a lot of effort on this one. Even so, we only measured 27 wells. We were out there measuring every minute that the completions were going on, and sometimes these last 2 weeks longer. So non-trivial. What'd we find? I'm going to group the findings and go over them very quickly, trying to save a bunch of time for questions. But we found four main things. First thing that we found was that well completion flowbacks, rather than being a large source, are now a relatively small source of methane emissions. And the reason for that is that you can do these completion flowbacks in a variety of ways, one of which is to employ what are called reduced emission completions. So you control what the emissions are. We made our measurements in 2012 and early 2013, and at that time the EPA was phasing in new regulations requiring reduced emission completions. By January of next year, for gas wells, reduced emission completions will be the law of the land. That's what will be required. They reduce emissions by 99%. We saw both completion flowbacks with and without the reduced emission completions, and this technology was really dramatically effective, much more effective than it was anticipated to be. So these emissions, much lower than people anticipated. Biggest surprise in the study was that a class of devices called pneumatic controllers were much larger than anybody thought they were. This was a big surprise because these devices have been around forever. They've been on wells for decades and decades and decades. And nobody was expecting this surprise, but we found that the emissions from this category were much higher than expected. For both this category as well as other categories, and one called in particular liquid unloading, what we found has a variety of names. I'm going to give you a technical definition, and then I'll throw out the jargon that's emerged around these. The concept is that you've got something like pneumatic controllers, and if you've got 100 of them, you measure 5 and you account for half of the emissions. The other 95, relatively low emitters. Right? There are a variety of names for this. This concept has been around forever with automobiles. People working in air quality have known for a long time, decades, that 10% of the passenger vehicles on the road account for 50% of the emissions. And you've undoubtedly driven behind some of these cars. All right? Same thing true here. Call them super emitters, call them fat tails, call them whatever you want. There's a small subset in many of these emission categories that account for a large fraction of the emissions. That's true for pneumatic controllers, it's true for leaks, it's true for liquid unloadings. If we then took a look at what people thought the emissions were before we started, here was the distribution. Here was the total, 25, 45 gigograms from this sector. Here's what we found. Same number, basically, within error bounds, 2,300 gigograms, but a very different distribution. Well, completion flowbacks becoming now consistent with new regulations, with the new source performance standards, small contributor to emissions. Pneumatic pumps and controllers, bigger than anticipated. Leaks, bigger than anticipated. We've gone out and done a bunch of additional studies that will be released sometime in the next month or so. But let me try and summarize what we've found from these top-down and bottom-up analyses. Top-down studies are telling us you're missing some sources. There are emissions out there that we're not accounting for. And there's regional variability in that. Study published yesterday pointed out a number of other things about these findings. What we find from bottom-up studies is that some emissions are lower than we expected, some are higher. We see regional variability, and for virtually all of these we have this fat tail in the distribution. Other things that just have been formally published yesterday include the idea that if you go out and you go to a site and it's part of the fat tail, if you go back a week later, it might have very low emissions, that these are temporally transient. Okay. So, we started this by saying, gee, we'd like to know, is the number between 1% and 6%? Where is it? So let's look. We can break the natural gas supply chain into a number of segments: production, gathering, processing, transmission, storage, local distribution, and so on. There are a variety of these studies going on. We've done a bunch of them here. Colorado State, in conjunction with Carnegie Mellon, is about to publish a bunch of things, as is Harvard, Washington State University, a number of others. What are we finding for these percentages? Our finding was that for this part of the supply chain, the leak percentage was about 0.4%. There are a variety of different ways of expressing that percentage. I'm not going to go into those so that we have time for questions. But if you look at what our current estimates are for some of these others, and there'll be more data coming out in the next couple of months on all these, the total that we're coming up with is that from the gas well to the power plant, the total is a little over 1% based on what we have right now. These numbers are subject to revision. The well to an end user is about 1.4%. So that's what we're learning now, is that this is not the big part of the supply chain. So we're actually quite close to around here based on our current knowledge. But again, it's going to be evolving over time. I think I'll skip that and just say that what we really need is measurements, and we need as many of these as we can possibly get. I've described to you a number of these measurements focusing on bottom-up studies, on top-down studies. We need many more of these, and hopefully there'll be a number of new initiatives that come up to get us much better data on methane concentrations. ARPA-E is about to announce a whole series of new methane monitoring networks sometime this month. But again, let me just close by saying that I've focused all my time today on greenhouse gases. They're not the only air issue, and air isn't the only environmental issue. This is a huge topic of dramatic environmental and economic importance, and we need as much information as we can get on this. And so I'm going to end there and see if you have any questions and try and answer them. So thanks for your attention.
Dave, thank you so much for very, very informative talk. This is something that we have tried to explore for quite some time, and we're glad you could make the time. My question is around the top-down and the bottom-up discrepancy. And it's a factor of 2. It's not a 10%, 15%.
Well, it depends.
So there is a gap. And so, if we discuss this in the public arena, how do we understand and explain that discrepancy?
All right, so I skipped over a couple slides, but now you have to see them. All right, so an important thing to recognize in looking at this top-down versus bottom-up is that a lot of times we're talking past one another. Let me give you an example. And I'll pick on my friends at NOAA, who are my friends, who I respect greatly. They do wonderful work. But when they made measurements over Los Angeles, what they reported was the methane that they saw in the atmosphere divided by the methane produced in Los Angeles. And they said the fraction escaping into the atmosphere, methane emitted in Los Angeles divided by the methane produced in Los Angeles is, I don't know, 7 to 16%. Huge number that they reported. And trying to say that the amount leaking from the natural gas production segment and normalizing by production in Los Angeles, given that Los Angeles imports 95% of its natural gas that's used in the basin, is really a meaningless number. You've got an extensive distribution section in Los Angeles, but a very different production segment. And using a single metric like that is really a disservice. what people tend to do is they tend to report a ratio. Emissions in a particular area that they've made measurements on divided by production rate. They have that single metric. And in general, they don't recognize that they're looking at different parts of the supply chain. So for example, when we did our study, we were just looking at the well sites. There are gathering sites down the road. There are processing plants down the road. We weren't making measurements on those. Right? Somebody flying in an airplane over that area will get all those sources. There are different spatial scales. We normalized ours over the entire country. Right? Others look at particular basins that have unique characteristics. There are different temporal scales. One of the challenges here is that if you take bottom-up inventories, the most recent bottom-up inventory that you can get today is from 2012. Right? So you're going to go out and make a measurement in 2014. What do you compare it to today, given how fast things are changing? All right? And then, typically people are reporting one number, all right, as a percentage, what fraction leaks. And to do that, you report a numerator and you report a denominator. So what's the numerator? Is it the annual emissions from all the sources in a region? Is it national? Is it the particular portion of the supply chain? Or is it a single well and you're going to extrapolate over the entire well life? These are all enormously different numbers, and in many ways we're talking past each other. To my knowledge, the few detailed reconciliations that have been attempted have actually come out not so bad. Now there are emissions that we're underestimating. That's clear. We're missing some. But I think a lot of it is just miscommunication. And so I've written a paper summarizing all these things. I'll forward it to you and not belabor this. Yes?
California in particular, how do you guys address in the calculation of emissions the fairly massive amount of natural migration from the Monterey Shale? I mean, there's hundreds of barrels a day of oil just from the basin, naturally.
Right, and so these measurements that I was citing from NOAA were over Los Angeles, but in Los Angeles you have the La Brea tar pits.
Same thing.
That have been there forever, exactly. And so among the sources that are really poorly characterized are natural seeps among them, abandoned wells as well, and a series of other sources that haven't been characterized all that well.
Is there even an attempt to, in some of these relatively hot basins, to look at the volume coming from these natural emissions? Because at one time, I remember ARCO put in hoods just capturing large volumes of natural gas coming out of the Santa Barbara Channel.
Yeah.
Tar balls on the beach are almost...
It depends on which investigators you're talking about. There are people who are going out there and trying to really get a good sense of what the natural seeps are, but not everybody does that. And so it's making for a very confused scientific literature. But in some ways it's hard. Once you go into an area and you start drilling, you don't have that unambiguous baseline anymore. So it's a real challenge.
I'd like to get some students. There we go.
Hi, thank you for coming out. Mm-hmm. The companies that were involved in your study, do they see mitigation of the natural gas leakage as a potential for increased profits? What's the cost-benefit factor as far as in placing mitigation factors versus the profit they could gain from controlling that gas leakage?
Right. So let's. There's a real nice report from ICF. It was commissioned by Environmental Defense. Looks at a variety of mitigations and tries to do a cost-benefit assessment. Let me give you some simple examples. So if you look, let's take pneumatic controllers. So for pneumatic controllers, this is one of those emission sources that has the fat tail. And if you say what is the value of the natural gas, valued at $4 per 1,000 standard cubic feet, that you would get from those emissions, just not emitting those, but keeping them in the value chain over a 3-year period, and it winds up being less than the cost of replacing that pneumatic controller and putting it in. So there are a whole series, and there are other things that are simple. You know, you go out and you have a leak detection program. If you can make it as cost effective as possible to go out and plug the leaks, very often the leak repair is a simple adjustment with very little capital cost. There are a number of things that would appear to have a positive economic return. In addition, I'll note that there have been public comments made by some companies, and I'll quote here Pioneer Natural Resources. As we were talking about these reduced emission completions for completion flowbacks, one of our colleagues from Pioneer made the comment, and this was on National Public Radio, that even if the EPA were not requiring reduced emission completions, they would do them anyway. And the reason they would do them anyway is because if you're taking the flowback that comes from a completion flowback and just putting it into a tank, you're getting the venting of all those things, but you're also not getting any information about how your flowback is progressing. If you flow to a separator and you get pressure and you get liquid flows and you get oil flows and you get a variety of other sources of information, that information has value. And for them, they argued that the value of that information was worth more than it cost to deploy the equipment, and hence they would do it anyway. So, you know, there are a lot of complex factors that come into this. I am sure we will see this aggressively debated. In April, the EPA issued a series of white papers on a number of sources in the oil and gas sector for methane emissions, and I think many people are anticipating that we will begin between now and certainly the next few months see a number of proposed regulations that I'm sure will get a lot of interest and comment. Yes?
I think from an industry perspective, the
Excuse
EPA...
Excuse me, sir. We have to use the microphone and we will go in circles. Sorry.
Yeah, over here.
Thanks, Professor Allen. My question is about the measurement of CO2 emissions, and it's not only in the natural gas industry, but also in general. What kind of uncertainty there is, and what kind of implications on pricing CO2 emissions? Thanks.
So I'll give you a simple answer, and then I'll give you a rationalization of that simple answer. The uncertainty bands in CO2 emission are much less on a relative basis. You know, what's the percent uncertainty? Than they are for methane emissions. And the reason for that is that the vast majority of CO2 emissions come from combustion. And we have good data on, you know, what's the mass of the fuels that we're burning and so on. And in contrast, the methane emissions typically in this sector come from leaks. And those are not bounded really in any way. So whether the leak is 0.1% or 2% can make an enormous difference in what the emission rate would be, and yet there's nothing physically that would bound you between those two numbers. And so in general, CO2 emissions are much more certain than the methane emissions.
Two questions. The first one is, do you know which service companies do REC mostly?
Well, now since it's the law of the land for gas wells at least,
Okay.
anybody who wants to stay in business is going to do RECs.
Okay, and then the second question is there any talk about moving away from like natural gas run pneumatic devices? Because you can also run pneumatic devices off of like air, in the air.
Sure.
Right?
And so, in fact, that's the norm in Europe. And if you go to a processing plant where there are reliable sources of electricity to do the compression of the air so that you can use it in a pneumatic device, that's the norm in the United States. But at many sites, they're quite remote, and it's just a lot easier to run it off of the gas that you already have at high pressure. You don't have to install a compressor on the site. But yes, people have thought about use air rather than the natural gas.
Great. We'd like to get one more student question. Any other students? Yep. Pass this back. Sorry. Thank you.
Thank you for the informative talk. I wanted to ask, what you've studied is only at the production stage, right? The emissions at the production stage. So is there anyone looking at integrating all the parts and like coming up with a number for the whole supply value chain?
Right. So let me sort of give you a chronology. Again, many of these studies were catalyzed by Environmental Defense Fund. My hat's off to them. They got involved in this when the head of the organization, a fellow named Fred Krupp, was invited by Stephen Chu to serve on an advisory panel for the Secretary of Energy. Stephen Chu was secretary at the time. And Environmental Defense Fund has for many years been worried about climate and, of course, was aware of methane. But I think that when Fred Krupp saw how really awful the data were, he initiated the largest research effort that I'm aware of any environmental group that's ever been done. And really dedicated his organization to this over the last several years. So my hat's off to them. We'll now have information, but let's talk about when, which was what your question was. So our study came out last year. There were a bunch of questions that were unanswered. We still had some sources that we saw we needed more information on, a particular source called liquid unloadings. We were also really interested in the issue of, well, why are certain pneumatic devices super emitters? What makes them super emitters? Why is that happening? And so we went out and collected a lot more data about the why. Gathering and processing segment is being done by Carnegie Mellon and Colorado State University. And they're also doing, Colorado State is also doing the transmission part. And that should be coming out in the next couple of months. The local distribution, if you go to the EDF website, there's actually some data posted already. It hasn't hit the scientific literature yet, but they've posted it comparing the leaks in the local distribution system in a place like Boston that has cast iron pipes versus Indianapolis, which has plastic pipes, versus New York City, which is in between those two extremes. Dramatic differences in what the emission rates are in these different regions. And then there are a few things like truck refueling and truck emissions, but this is the supply chain. These will all be out within a few months. The expectation is then that certainly EDF will write a synthesis paper, but once all these data are out, I'll tell you from experience, everybody will use the data, and that there will be an enormous number of syntheses that get done. So expect that to happen beginning early next year and possibly sooner, depending on when EPA comes up with these proposed regulations.
Any other student questions before we open it up?
We can take two more questions, one from Dave and one from Ashley.
Thank you for joining us. Very good. Are there any specific characteristics of the super emitters, or is it sloppy workmanship, defective components, smaller scale firms versus larger? Any general characteristics there?
All of the above. We're commenting on it particularly for pneumatic controllers. You can also think about, I'll give you some examples that have been observed here in Texas and been documented already that are not sort of still in the peer review process. So if you go up to the Barnett Shale and you ask which sites are super emitters, and then take a helicopter and fly over some of those sites and image them with a thermal imaging camera, an IR camera, which gives you a visible image of something like a methane plume because of its temperature difference. What you will see is the biggest emissions coming off of storage tanks. That can be because you've got a stuck dump valve. It can be because your pneumatic controller on your separator is not working properly. It can be because of a number of things. There are also, in some cases, older equipment that's out there. Another example, compressors. You go out and you look at certain compressors that have seen, in some cases, 50 years of service, and look at the rod packings on those, and if they're not carefully maintained, you can get some very large emission rates. There are other operating practices. It's a whole range of things, but in general, it's not something that we don't know how to fix. Once you've identified it, we know how to fix it. The question will be, how much will it cost, and what are the emissions relative to the cost? Student question in the back?
Yeah, I had a question really about your opinion after having done all this field work, but generally about here in Texas and the Railroad Commission, and just based on your work out in the field and all these sites, is in your opinion, is the Railroad Commission currently structured in such a way that it's up for the task of regulating an industry that, like you showed, has grown exponentially since 1990, or perhaps should legislatures be thinking about ways to maybe sort of address the regulatory structure here in Texas?
All right, I'm going to give you I'm going to rephrase your question, because in the domain that I work, the Railroad Commission is not the regulatory agency. It's the Texas Commission on Environmental Quality. So they are responsible for what the emissions are, and as well as in some cases local jurisdictions. And so let me just tell you a somewhat different story. So I came to Texas from UCLA in '95. I'd worked for a long time in Southern California. And around the time I got here, Houston, and this was in 1999, Houston had just surpassed Los Angeles as having the worst ozone problem in the United States. And the state was about to embark on to fix that problem, was about to embark on what was going to be the most costly program for reducing ozone concentrations that had ever been done anywhere in the world, and the most aggressive regulations that would have been required anywhere in the world. And so what was decided was that we should organize the best possible scientific campaign to make sure that we were getting the science right before we did that. And we did that. And what we found was that our notions of what the problem was were incorrect. And that if we had proceeded without having really rigorously investigated the science, we would have solved the wrong problem and spent billions of dollars a year and still had a serious ozone problem in Houston. Instead, we found out what needed to be done. The Texas Commission on Environmental Quality took quick action and instituted a program that you see nowhere else in the world for limiting certain types of emissions of certain compounds, now referred to as highly reactive volatile organic compounds, a term that really only applies in the Gulf Coast in southeast Texas. And we come back 6 years later and then 10 years later, do follow-up studies. And Houston now doesn't even have the worst ozone problem in Texas. It has, that distinction goes to Dallas. And so my experience with the Commission and with the regulated community is they want to make sure they're going to solve the right problem. Right? And I think here the challenge, and much of the debate will be, all right, the science now tells us that we've got these super emitters, we've got these fat tails out there. What do? Do you go out and fix every pneumatic controller, make every pneumatic controller an air controller? Do you target? I think that there's going to be a really robust discussion about that, but I think the sense will be, at least based on my experience here in Texas, if your facts are robust and you really understand the problem, then my experience has been that we're very effective at solving it. But my experience also is that there's a demand that we understand what we're trying to solve. So.
This has been a terrific afternoon of discussion. Thank you so much, Dave, for making it happen.
Thank you.